All right, welcome back to part 3. So now we're going to address the assumptions that need to be met when we're doing a bivariate correlation. So the first assumption is that the data are continuous. So the level of measurement is interval or ratio. And you'll be very used to this because it's the same thing of other parametric tests like a t-test or an ANOVA. But we are going to address what do we do if one of the two variables in our correlation is not continuous. There are some special correlations that can handle that. And those specifically are the bivariate and biserial and point-biserial correlations. So these are special correlations. When one variable is continuous, that's normal. That typically both are continuous for Pearson's correlation. But if one is continuous and the other is categorical, specifically with two categories, which we also call dichotomous, then you can perform a biserial or a point-biserial correlation. So what are examples of dichotomous variables? You can be pregnant or not pregnant. You can be dead or alive. And we're not going to think too deeply about these because if you were doing a scientific study and you were counting people as either dead or alive, you wouldn't record someone as almost dead or super alive. It's dichotomous. You're either dead or alive. Female or male, if we kind of ignore intersex for now. Retired or not retired. Pass or fail. When you flip a coin, is it heads or tails? And you could ask people, are you Democratic or Republican? So when do we use a point-biserial correlation and when do we use a biserial correlation? A point-biserial correlation is used when that dichotomous variable is discrete. In other words, there's no underlying continuum between those two categories. So examples from our previous list, you're either pregnant or not pregnant. You're either dead or alive. When you flip a coin, it's either heads or tails. I find if you think too long about any of these, you might start saying, well, what if I flip a coin and it lands on the edge? And let's not worry about those things. Let's just say that these are fairly discrete dichotomous variables. A biserial correlation, in contrast, is used when there is an underlying continuum between your dichotomous variables. Examples here are female or male, and that is a continuum, whether you're talking about sexual organs, hormones. If you're intersex, you're somewhere in the middle of this continuum, so that is, there is an underlying continuum to that dichotomous variable. Are you retired or not retired? So some people may be retired from full-time work but still pursue part-time work. So they fall in the middle. Did you pass or fail? And that's the example we'll look at here. Because it's possible to fail by 1%, but you can also fail by 20%. Likewise, you can pass by 1%, or you can pass by 10%. Democratic or Republican also has a continuum. You can be considered to be to the left, the right, or far right of being Democratic or Republican. So how do we do a point-biserial correlation? So here we denote this, we still use the letter R, and then we use subscript PB to denote point-biserial. This is actually the easiest to do because SPSS will do it for us. You simply rerun Pearson's correlation with your continuous variable, and then for your dichotomous variable, you simply code it as 0 and 1. And it will give you a Pearson's correlation, which is equivalent to a point-biserial correlation. So that's the easy case. Slightly more complex, what do you do if there is a continuum, say this pass or fail situation, which we'll run an example of? Well, you start by doing a point-biserial correlation, which in SPSS is just a Pearson's correlation. You would get that value, so the R sub PB, and you would plug that into this formula. The other things in this formula is you need to know the proportion of your two groups. So maybe one of your groups is 40% of the data set, so your p-value would be 0.4. And that would make the other half, or the other proportion of your participants 0.6. So the q value would be 0.6. So you multiply those by each other, take the square root, and you divide by y. Now what is y? This we look up from the normal distribution with values p and q. And we'll look at that example in a second. From the textbook, when they talked about the biserial correlation, they actually referred to some of the online resources, and this is the website It's the online resources for this textbook if you want to read more about the biserial correlation. But let's try one for ourselves. So let's go back to the data set we're already working with. We have your attendance. That is a continuous variable. And now instead of looking at your grade, let's just make this dichotomous. Let's look at whether your grade was above or below 80%. And I picked 80% because it had a more even split in the class between just pass and fail. When I did pass or fail, only a handful failed, thankfully. And I thought it'd be more interesting if we had a little more even data set between our two dichotomous variables. So because there is a continuum between passing and failing, we should do a biserial correlation. And our first step is to run a point-biserial correlation, and in SPSS, that's simply a bivariate Pearson's correlation. So I've recoded our data, and because we have SPSS here, let's go look at it. So the absences, this is exactly the same as before, but now instead of a grade, I recoded these to be 0 and 1. Ooh, I think 0 meant below 80% and 1 was below 80%. So we just want to go through and run a typical correlation, which will actually be a point-biserial correlation. So we'll say bivariate. We want to correlate these two variables. We're going to be using Pearson's, and let's ask for some means as well. We say OK. So here's our output, and you can see here the point-biserial correlation. The R value is negative 0.516, and it happens to be a significant relationship, although that doesn't really matter in this circumstance. So let's go back to our slides. So done. We've got our first step. We ran our point-biserial correlation. Now we need to use this formula. So there's the data. They're up on Blackboard too. And this is the exact same thing we saw in SPSS. So the data that we're going to use are the point-biserial correlation, which is negative 0.516. The other thing is you need to look at how many students fall into your two categories. So 53 out of 82, can't remember if that's above or below 80, but the proportion there is 0.6463. You could simply do 1 minus that to get your other proportion, but I did go through and count. There were 29 students in the other category. In case you're wondering, why is this out of 82? Before it was out of 87, right? Well, when we look at our next assumption, we're going to talk about outliers and removing outliers. And I actually went ahead and removed 5 outliers from this data set before running the point-biserial correlation. Okay, so back on track. We're trying to run our biserial correlation, which involves this formula. And we know 3 of our 4 variables. We need to look up y. And if you use the appendix in your textbook, the first appendix, you'll find y is 0.3712. So what you do in this appendix, it's a long list. There's lots of z values, jz, yeah, z, jz values. And you need to look up the large proportion and the smaller proportion. And that's what p and q are. So whichever one is bigger, that's your larger proportion. And for us, it is 0.6463. So that exact value is not on the table. It falls somewhere between here, and it's a little bit closer to this value, so we're going to use it. See, that smaller proportion is very similar to our Q. Here, I'm going to move my face out of the way here. Okay, and there, that's the Y value. So that's how we get that Y. Sorry, wrong Y value. Here's our Y value, 0.3712, based on a larger proportion of 0.64803. Okay, great. So we plug all of that into our formula, do that math, and we find that our biserial correlation, so we still use the letter R, but we put a subscript B to denote a biserial correlation, is negative 0.665. So there are ways to look at correlations when one of your variables is not continuous. If both of your variables are not continuous, then you can't run your typical correlations. You're probably going to get into non-parametric tests, which we're not going to cover. Back to our assumptions. So let's move forward, assuming that both variables are continuous. The next thing we need to do is look for outliers, and this is something we've also done in our other tests. This is most easily done with a box and whisker plot. And the solution here, for t-tests and ANOVAs, it was, well, look what is common in your area. People probably leave them in. Correlation, the tendency seems to be to remove them because outliers can heavily influence your correlations. So outliers are typically removed. You might see a data transformation used to minimize that outlier. And if you really have a rough time with the outliers, then you may be forced to do a non-parametric correlation. So here are two box and whisker plots, both for absences and for grade. And you can see that we have several variables. So absences, there's looks like 4 different students who had a lot of absences. And for grade, there are 3 different students who had particularly low grades. And actually, some of these data points are identical. So 34 and 44 are outliers, both in absences and in grade. So in the end, I think there's actually only 5 outliers here because some of them are outliers in both variables. So if we go back to our scatter plot, what I did is I just highlighted those outliers. Oops. So our original correlation with those outliers, if you remember, was negative 0.757. Now let's remove those 5 outliers. There's actually another data file online with those 5 outliers removed. And we can rerun the correlation. I won't take you through SPSS this time, but we see that the correlation is still significant, significantly different from no relationship. The correlation still has a large effect size, but the R value has decreased a bit to negative 0.601. So only one more assumption, thankfully, and that's that our data are normally distributed. And we've seen this several times before as well. So you can look for this in several ways with histogram, those PP or QQ plots. You can measure the skew, kurtosis, and then finally the 2 statistical tests, the KS test for making that easier to pronounce, and the Shapiro-Wilk test. Now, those tests are typically not needed when your sample size is larger than 30, because you should have a large effect size, and the central limit theorem suggests that they will be normally distributed. If it's less than 30, you can use these tests. The problem is that they're typically underpowered. So they might say they're not significant, but that might only be because it's an underpowered test. What are the solutions here? Well, again, data transformations can potentially improve the normality to your data. We're actually going to talk about a data transformation soon. And lastly, kind of your other resort as well, if I fail this assumption, I'll go to a non-parametric correlation that has less assumptions. And that is the end of part 3.